Welcome to the video for Lecture 25, Section 2. This video introduces you to the payday approximation used to model process delays or process dead times. This section also includes a new way to write MATLAB commands for servo and regulator problems that is more convenient than the method used previously. The video also discusses how to handle multiple process delays in different parts of a control process.
In the bioreactor section, we introduced a sample line delay. We said that the reactant A analyzer needed to be kept in an environmentally controlled room that was 15 meters away from the outlet from tank 2, and there was a sample line delay because it took 30 seconds for the sample taken from tank 2 outlet to reach the analyzer. There are other types of process delays or process dead times that can occur. So while sample line delay and sensor location are common, be aware that there can be other reasons for process delays in the control system. We said that we would approximate the delay by multiplying the appropriate transfer functions by e to the minus time delay, td, times s. This was based on the translation of function Laplace transform, and the s term is for the Laplace domain s, not s for seconds. For the bioreactor, we had a 30-second delay, so the expression was e to the minus 30 times s. And we added a transfer function for the time delay to the block diagram in the sensor feedback part of the diagram. This video will describe how to add the sample delay in MATLAB commands to model the process time-dependent response with the delay. I will use the water heater process to illustrate how to add the time delay. We will handle the servo and regulator problems separately to keep the transfer function simpler. With the servo case, Ti equals 0. Again, to simplify the problem, we will assume the actuator gain kV equals 1 and the sensor feedback element Km equals 1 because tau m equals 0. For this example, we will place the time delay in the sensor feedback element. At the bottom of the slide is the transfer function for the servo problem. On the right end of the equation is the delay transform g delay that we multiply times the servo problem transfer function. The method we will use to approximate sample line delay and process dead time is to use a first-order payday approximation of the e to the minus time delay times s. The expression used is shown here. The first-order approximation in the Laplace domain is 1 minus td over 2 times s over 1 plus td over 2 times s. The terms are the same, but the numerator has a minus sign and the denominator has a plus sign. The MATLAB expression to define the first-order payday transfer function is also shown on the slide. The expression for g delay is tf left parentheses left square bracket minus td over 2 space 1 right square bracket comma left square bracket td over 2 space 1 right square bracket right parentheses. The variable td is the process dead time. We will multiply the servo problem transfer function by this dead time transfer function. For your information, there is a second-order payday approximation in the course packet that could be used. This slide shows the servo problem transfer function with the process delay function on the far right of the equation. Notice that the transfer function is written using variable names for the different transfer function elements. The actuator is kV and the sensor feedback element is h. The process term we are using is g and the process delay term is g delay. Kp is the term for proportional control. We can use this approach in MATLAB to reduce the amount of work we need to do. In MATLAB, we can simply write the step or impulse input change command using a similar format after we define the transfer functions. The second line shows how to write the command calculate the time-dependent process output y1 for a unit step change in TR, and as we did in the equation above, we add the process delay transfer function to the equation. The final term t is the time array we have defined for the problem before. Here are also the 6 MATLAB commands we need to write. In the first line we define the time array that goes from 0 to 300 in increments of 10 and set td equal to 30. In the second line, we define G1. This is defining the controller transfer function which, because we are using proportional control, is simply the constant Kp equals 82.76. The next line defines the transfer function for the actuator and the feedback elements. Again, because we have simplified the problem, they are constants in this case, and both Kv and H equal 1. If we had used first-order response equations with the time constants, we need to write the expressions that define the first-order transfer functions. The next line is a better example showing how to define a transfer function. This line defines G3. G3 is the transfer function for the heating process for the servo case. The numerator, 0.02427, which is equal to 1 over rho times V dot times C sub P. The denominator is tau P times S plus 1 for our first order fluid heating process. In this case, tau P is 120 seconds. The next line defines G5, which is the equation for the first order payday approximation of a process delay. The variable Td was defined and set equal to the time delay, 30 seconds in this case. The final line is the MATLAB command to fill the Y1 array, which is the time-dependent response to a unit step change to the transfer function defined by G1 times G2 times G3 times G5 over 1 plus G1 times G2 times G3 times H. Then at the end is the time array. The advantage of using this method to write the MATLAB commands is that you can change the process control equation described by G1 or one of the other process elements without having to change this equation for calculating Y1, and you do not need to calculate out the transfer function coefficients. Here is the information for the regulator case. The product of rho times V dot times C sub P is 41.38. Again, we multiply the regulator case transfer function by the transfer function for the process delay given by G delay. The time-dependent response to a unit step change is given by 41.38 times G over 1 plus Kp times Kv times G times H, and that is all multiplied by G delay. The last MATLAB command fills the array Y2 with the response of the transfer function described by G4 times G3 times G5 over 1 plus G1 times G2 times G3 times H. The time array is given by T. This slide shows a graph that plots Y1 and Y2. These are the time-dependent water heater responses to unit step changes in the set point temperature for the regulator problem and a unit step change in the inlet water temperature for the regulator case. Both cases have a 30-second process delay. The dip below zero is an artifact of the payday approximation. It does not mean that the temperature dips below zero. It can be clearer if we cover up the material below the zero temperature. The way to interpret this is that the response is delayed by 30 seconds, and the temperatures at 0 and above after the first 30 seconds represent the process output. The offsets shown here and seen before are a consequence of proportional control only. So let's say we want to get rid of the offsets we get using proportional control alone, and we decide to use proportional plus integral control. One way to model this is to write the integral expression and multiply it times the proportional control constant. The MATLAB command is TF, left parentheses, left square bracket, tau I, space 1, right square bracket, comma, left square bracket, tau I, space 0, right square bracket, right parentheses. This graph shows the servo and regulator problem responses to a unit step changes with a 30-second process delay and using proportional plus integral control. As we expect, the servo case settles down to a final value of 1, the new set point temperature, and the regulator case settles down to 0 after a 1 degree change in the inlet water temperature. Again, the data below the 0 temperature is an artifact of the payday method and do not represent real values. This slide shows one of the simplified block diagrams for the bioreactor problem in section 21. It has several of the process constants incorporated into the terms. We have a 30-second process delay due to the sampling delay in the sensor feedback line. The MATLAB commands to solve this problem and to plot the time-dependent responses with and without delay are given in the course packet. This slide shows the time-dependent servo problem responses with and without the process delay. The solid line without markers is the response with the delay. Again, the response with the delay has points below 0 between 0 and the 30-second point. These are an artifact of the process and do not represent a real response. Again, a better way to think about it is to cover up the line between 0 and 30 seconds. If I cover up the delay response between 0 and 30 seconds, it is easier to see how the response is delayed. It is interesting to note that the delayed response has less of an overshoot compared to the no delayed response. The time to settle down appears to be about the same. So far, all of the process delay examples had the delay in the sensor and feedback part of the process. What if the delay is in some other part of the process? What if the process dead time was in the inlet fluid temperature? Let's say that it takes 30 seconds between when the inlet fluid temperature change actually reaches the process. How do we represent that in the block diagram and the equations? So let's look at a case with a single process delay in the inlet part of the process. In the block diagram, we add the process dead time into the inlet line. If, as we said, the delay was in the inlet fluid temperature, we add the e to the minus 30 times s term to the line between G4 and the summing point. Note that this block diagram does not have a delay in the sensor feedback part of the process. In the equation, we add the delay term to the regulator case problem. Here is the block diagram with the delay in the inlet fluid temperature and the servo problem equation. Note that there is no sensor feedback delay. The delay is in the inlet fluid temperature. In this case, the equation does not have a delay transfer function because the delay does not impact the servo part of the process. So the location of the process delay does impact how and where delay or dead time terms are included in the process transfer functions. There can be process delays in the sensor feedback part of the process. They can be in the inlet part of the process, can be in the cascade controls part of the process, or in the feed forward part of the process. In each case, add the block to the right part of the block diagram and include the delay transfer function in the appropriate transfer function. This slide shows how to handle multiple delays. Let's say we have a 70-second delay in the sensor feedback part of the process. We add a transfer function with e to the minus 70 times s to that part of the block diagram. This delay affects both the servo and regulator processes because both equations involve the feedback element in the equations. Now if we have a 20-second delay in the inlet, we add the transfer function to the block diagram and we add this term to the regulator part of the response. This inlet delay does not affect the regulatory part of the process. So if you look at the equation, the 70-second delay is added to both the servo and the regulator parts of the equation, but the 20-second delay is only added to the regulator part of the equation. And when I say add, I mean the delay term is multiplied times the expressions. This brings me to the end of the Lecture 25 video. Write down any questions you have and bring them up in class.